In the last videos, we've learned how to use MATLAB to connect to a camera. Then we learned how to get a single snapshot from that camera. And then we learned how to detect objects by color. We also learned how to use a center of mass type approach to find the location of that object in units of pixels and show the location of that object on the screen. In this video, we're going to look at the case where the object that we're looking at is not a particular unique color in the field of view. There are many methods that you can use to find an object that is not a particular unique color. The method that we're looking at in this video is called background subtraction. Background subtraction is a method that works well when the camera is not moving and the background, that is, the objects in the image that are not of interest to you, stay constant over time. And objects that are of interest to you, what we call the foreground, come into and out of view. I've started my code here with the same introductory lines that we've used in the past. I have one line of code for creating a variable called vid to connect to the camera. Then I set the color space of the camera to RGB. Then we open up a preview window to see a live image of the video, which also starts the camera equalizing its light levels. Then we have a 3-second pause to wait until the light levels of the camera have equalized. Now here's how background subtraction works. We're going to first take a picture with no objects of interest in the view, and we'll call that picture the background. Then we'll wait until an object that we want to detect has come into view, and we'll take a new picture. We can then subtract the matrix representing the background from the new image we've taken, and this should leave us with just the new object that we want. Let's try doing it to see how this works. After the light levels in the camera have equalized, we want to take an image that will serve as the background. So we're going to create a new variable called background equal to getSnapshot vid. Now note that this snapshot that we take will be a full color image. We'd like to reduce the amount of data that we have to process and simplify our results. So instead of having a full color image, we'd like to have a grayscale image. We've already learned a couple of ways of converting from color to grayscale. One of those ways is to isolate one of the 3 colors. We could have a single grayscale image that represents only the red level, or a single grayscale image that represents only the green level or the blue level. But there are other ways to convert to grayscale that might be more useful to us. We've learned in the lecture videos that we can convert to grayscale using any kind of a combination of red, green, and blue images that adds up to 1. In fact, MATLAB has a built-in function for converting red, green, blue to grayscale, and that function is simply called RGB to gray. If we put getSnapshot in the parentheses of RGB to gray, MATLAB will use its function for converting the red, green, blue image to grayscale. I'm going to open up the MATLAB help, and we're going to take a look at what this function does because it's pretty interesting what kind of a function MATLAB uses for the color to grayscale conversion. So I'm going to open up the help. I did this by clicking on the question mark up here. And I'm going to type in RGB to gray. Convert RGB image or color map to grayscale. If you look at this help page and you scroll down the help page to where it says more about and then algorithms, expand algorithms. Here it shows you the equation that MATLAB is using to convert RGB to gray using this function. You'll notice that each of these weights, if we add them up, they add up to 1. So it meets our requirement for how to convert an RGB image to a grayscale image. These seem like very specific weights that have been put in front of R, G, and B. How did MATLAB come up with these numbers for each component? These numbers have been chosen to most closely represent the way the human eye sees. As it turns out, the human eye does not perceive the colors red, green, and blue equally. By making the weights unequal in this way, the grayscale conversion that we get will most closely represent the function of the human eye. So this is the red, green, blue to grayscale conversion that we're going to use here for our background. Now, after we've captured the background, we need to wait until an object of interest has come into the field of view. In our example, we're going to wait until you, the user of the program, have placed the object in the field of view. So to allow for that, we'd like to pop up a message window informing you that you should place the object in the view and then waiting until you click a button to indicate that you have finished placing the object. In order to communicate to the user that it's time to place an object in the field of view, we'll use MATLAB's function messageBox. With messageBox, we can put some words in single quotes, and when we run this code, MATLAB will pop up a message window with an OK button that displays some kind of a message. So for this message, let's type in place an object in the field of view, then click OK. Now we would like MATLAB to wait and not move on to the next line of code until we have clicked OK. So we need to add something else here. We're going to add in the command wait for, and we'll put this whole message box in parentheses. This way, when MATLAB displays this message box, it will wait on this line until we have in fact clicked OK. So after we click OK, indicating that we've placed an object in the field of view, the next thing that we would like MATLAB to do is take a new image. We'll use the variable frame for this image. So frame will be equal to get snapshot vid, and once again we need to make sure that we convert this color image into an RGB image. So we'll use the function RGB to gray to convert this image to grayscale. So now we have one variable called frame that includes both the object that we've placed in the view, and we have another image called background that is everything that we're not interested in, an image without the object in the field of view. To find just the object by itself, we need to take the variable frame and subtract the background. We'll call this the foreground. Now, once we're done, let's put in some code to show all of these different images that we've taken. Rather than popping up a new window every time, let's use MATLAB's function subplot. We'll create a new figure window. We'll call it figure 2 because we already have one image showing the live feed from the camera. Then we'll create a subplot. Here we can say how many rows and how many columns of images we want in this one figure. Since we have a background image, a frame, and a foreground image, let's have 3 rows of images, 1 column of images, and then the third number we type in is which image this is, the first, second, or third image. So this will be the first one. And what we want to show in this image is just the background. Next, we'll create the next subplot. 3 rows, 1 column, and now this is the second image that we're showing. Here we'll show the frame that has both the object and the background. And finally, for our third plot, let's show just the foreground. Okay, let's run this code and see what happens. We get a live feed from the camera. Then we get a message box that comes up telling us to place an object in the field of view and click OK. I'm going to use one of our little 256 nuts, and I'll place the object right there. Once I've placed the object, I click OK. And here we have our 3 images. The first one is our background. It looks just like I expect it to. The second one is the frame after we've placed the object, and it looks like I expect it to with the nut in the center. But the third image is not showing the nut at all. Can you hypothesize why this is? To understand why we don't see the nut, think about the values of each pixel in these 2 images. Remember that each pixel holds a value between 0 and 255. 0 means totally black, and 255 means totally white. We calculated this third image by taking the second image and subtracting the first. Our nut, since it is black, has pixel values around 0, while in the first image, those pixel values are much higher because they're closer to being white. In order to solve this problem, let's go back to our code. Instead of doing frame minus background, let's do background minus frame. This will better allow us to detect a black object rather than a white object. Now, before we run the code again, make sure you remove the nut from the field of view so that we are ready to capture a background image. Then click Run. Here's our live feed. It's waiting for me to place an object, so I'll place the object. Then I'll click OK. There we go. This time we were successfully able to detect the nut, which you can see right in the center of the field of view. Can you find the location of this nut now that we have this image where the nut is white on a black background? We can use the same code that we developed previously to find the locations of the colored objects. Rather than redeveloping this code all over again, I'm going to go back to the code we had previously. and I'm going to copy the column location and row location calculations that we did before. And I'll paste them here. Now, instead of doing a color only image for this calculation, we're going to do this calculation on the foreground image. Now, let's try running this code again. But we also need to have the line of code that plots the location of the object on the image. So I'm going to take this figure 2 and I'm going to cut it from where it is, and I'm going to put it at the end instead. Then on this foreground image, I'm going to turn on the hold. Then we will plot. First we need the X location, and X location will come from the column. And the Y location is based on the rows. And we'll stick with our red X for now. And then I'll turn the hold off in case we want to plot something else on top of that. I will remove the nut from the field of view of the camera. Here we get our live feed and then a message box telling us to place the object in the field of view. I'll place it some other location here and then click OK. Let's zoom in on this location. It looks like it didn't do very well here. The X didn't get right at the center of that object. One reason that can happen is if the light levels of your camera change between capturing the background and capturing the foreground, you can have pixels that appear dark here but actually have low values which skew the location of the X. You'll notice when I put my hand in the field of view and then take it out, the light levels change. This can be causing a difference in what I get for the foreground and for the background. Errors can also be caused if the camera moves at all between your background image and your foreground image. That will cause error. To help us understand why the nut location is not very good, let's take a look at the matrix that's held in the variable foreground. As we scroll through the variable foreground, we see that a lot of these pixels are 0, which is what we want. A pixel value of 0 is a perfectly black pixel. However, some of the pixels are not perfectly black. We see grayscale values scattered in throughout. We could improve our object detection by getting rid of these values that are very small. This is just image noise that we're picking up. Here's how we can do that. After we calculate the foreground by doing background subtraction, we're going to threshold the foreground image. We only want to keep pixels that are greater than some value. Let's start by setting our threshold to 50. Now, let's test our object detection again. Remove the object from the field of view and run your code. Here we see that the location of the X is much closer to its actual location. We achieve this by eliminating much of the image noise. The image noise is scattered pixels throughout that have a low value but actually do not represent the nut. In effect, we've converted our grayscale image to a black and white image, where any pixel that has a value greater than 50 is converted to a value of 1, meaning a light pixel, and any pixel that has a value less than 50 is converted to 0, that is, a black pixel. We've reduced both the amount of information in the image, and we've also reduced the amount of image noise.